Anyway, one of the most common ways to define consciousness, which is one of the big words in my title, is this awareness. And one of the things that we're most aware of is the content of our sensations, what we perceive in the world that's around us. And my goal for tonight, or one of the goals, is to give you a knowledge of and some appreciation for some of the issues that are involved in looking at that relationship, the relationship between our sensations and our consciousness. And I'm going to talk about 5 issues, 5 problems, but there are lots more. There are always more problems. But perhaps those will be topics for a future talk. The 5 I'm going to talk about tonight are somewhat idiosyncratic, but I think they're also representative, and hopefully you'll find them interesting and thought-provoking. We could easily do a full evening on any of the 5. One of the main points that I hope you leave with tonight is that the correlation between what our senses tell us is out in the world and what's actually out in the world is not nearly as high, not nearly as perfect as you might think, as you might hope. I'm going to take 2 main approaches. The first is going to involve talking about some empirical findings, and we're going to do some demonstrations in here involving a few different perceptual phenomena. That's mainly going to be the first portion. The second portion, we're going to look at some philosophical issues in considering the nature of the relationship between sensation and consciousness. And whenever possible, I'll throw in some miscellaneous scientific findings that are relevant, because that's what I do. I want to give you a couple sentences about my background on this topic. Most of you probably already know. For much of my career, I taught graduate and undergraduate classes in sensation and perception, and in cognitive psychology and related sorts of classes. I also taught classes on consciousness studies, lifespan development, psychology of music, philosophical foundations of psychology, various other courses. For 13 years at TCU, I directed the research laboratory studying dynamic aspects of perception and cognition. And we looked at some topics that are relevant to some of the things that we're going to talk about tonight. So kind of a major thread of my scientific work has been kind of on these and some related topics. So what are these 5 issues, these 5 problems? Here are the 5 problems: subjective contours, context effects, ambiguous reversible figures, phantom lens syndrome, and the nature of qualia. You probably don't know what a lot of those terms mean, but don't worry, you soon will. Okay. So let's start with subjective contours. Here's one of the most famous examples. I'll give you a moment to look at it and decide what you see. What do you see?
2 triangles.
Very good. Anybody else?
I see 3 emoticons trying to eat an empty space.
That's what I was thinking.
You played far too much Pac-Man.
Yeah.
Pac-Man, that's what it is, Pac-Man.
3 incomplete triangles and 3 Pac-Man.
It's good you're saying this because you're anticipating the 2 directions I'm going to go. You probably see a border right there, there. And this central white triangle probably looks brighter than the background. That's not what's in the display. Okay, what's in the display is just some black figures. Now, when I used to use this demonstration in class, I had it on a plastic overlay, just black print. You could put it on, it was much more obvious. For now, since it's on a monitor, I have to take my word for it, that white's the same as that white. Okay. But your brain doesn't see it that way. Your brain imposes this white triangle on top of this black outline, resting on top of 3 circles. That's a relatively simple interpretation. The other interpretation, John's already alluded to. You've got a Pac-Man figure, actually you've got 3 Pac-Man figures, and they just happen to be lined up to where the openings line up with the openings on the other Pac-Man figures. It's a remarkable coincidence. On top of that, you have these 3 angle shapes, and the ends of the angles happen to line up with lines that you would draw between each of the Pac-Man shapes. Again, a bunch of coincidences. That's a lot of coincidences. Your brain doesn't like coincidences. Okay? Your brain likes things simple. So it opts for the simple interpretation of this kind of figure instead of the one that requires a lot of coincidences.
Could that be,
Say that again.
I'm sorry. Could that be our
Okay,
desire?
come in, have a seat.
Could that be our desire to have air?
Somebody come in and come in chairs.
Thank you.
So sorry, we like got lost.
Oh, no problem.
That can happen.
Yeah, we did.
Not a problem. Actually, this is the first sort of content slide, so you have to just just to quickly catch you up, look at this figure. And I'm going to guess that you're probably going to see boundary lines here. You're going to see a white figure on top, or sorry, white triangle on top of a black outline. That white triangle is not actually there. Okay. Instead, it's the configuration of all these sorts of elements that implies it's there. Well, your mind puts it there, so there's sort of a disconnect here between what that figure actually is, what the stimulus actually is, and what you're aware of and what you perceive. And the more evidence there is that there should be lines there, okay, the stronger the percept becomes. This is true for 3D as well as 2D. So on the left, you probably see an illusory white sphere. Well, there's no white sphere. Okay, the only thing that would be printed on the screen, okay, are the black cones. Okay, there are a lot of cones, and they're all positioned to suggest the presence of a sphere. And since they're all positioned that way, again, that's a much more parsimonious interpretation than having all these cones just sort of randomly by chance lining up to suggest a sphere. You can see in the graph on the right, the more evidence there is that there should be a contour, the stronger it looks. So here, these little Pac-Man shapes are relatively smaller. There's not quite as much evidence that there would be a white square on top of them, but as those black shapes get bigger, more of them is occluded, which gives you more evidence that there should be a contour there. And in fact, this white square probably looks brighter to you than that white square. And those contours look stronger on the right figure than on the left. Does that work on a monitor, by the way?
Yes.
Okay, good, good. Okay, where are we? So the appearance of these kind of subjective contours suggests our perception sort of prefers to interpret stimuli in the simplest way possible. This is consistent with what is known as Gestalt laws of perceptual grouping. This is something that you'll probably get in Psych 101 if you've had that. And you can see several of these Gestalt laws on the right side of the slide. They concern things like proximity, similarity, good continuation, and so on. And they describe how you spontaneously, automatically organize the visual inputs that you see, how you organize your perceptual world. So for example, you're more likely to perceive the 8 black dots in the top row as 4 pairs. And that's because of the spacing, or proximity between different dots. Law of similarity suggests that items that are more similar are more likely to be grouped together or perceived as part of the same object. So you're more likely to see the second row as alternating pairs of black and white. Okay? Good continuation would suggest that you're more likely to perceive this as being 2 lines that happen to overlap instead of 2 V shapes that just happen to have their vertices at the same spatial coordinates. You're going to see this as a straight line and a curved line rather than separate lines that have all their endpoints just happen to line up perfectly to where you get that. Several others there that you can look at. Basically, these are mechanisms that you either learn very early or built in. We're not quite sure which yet. But you will use these when you look at visual scenes, and it helps you figure out, figure from ground, objects from background, and that sort of thing.
Can that be like a survival mechanism when you put things together fast? Because
Well,
if
it
you
could-
didn't do it,
It couldn't hurt. I'll
you're
put
in
it that way.
danger.
Yeah. A lot of things like this, people have argued that they have been selected. They're very adaptive in terms of coping with what the environment might happen to throw at us. So yeah, you could certainly make an argument that being effective in figuring out figure from ground could be adaptive. So the short answer is yes. Where are we now? The idea is that the interpretation of your sensations is the simplest possible. Now this is what's referred to as the principle of Pragnanz. Pragnanz is a German word here. The simplest organization requiring the least cognitive effort, and that's a key too. Okay, one reason why we tend to prefer the simplest kind of explanation is because it's the easiest explanation.
Saves time.
Think about describing that triangle. You can talk about a white triangle on a black on 3 circles, as opposed to the 3 Pac-Man shapes that all happen to line up just right and yada, yada, yada. Okay. Takes a lot more time, a lot more effort, and by and large, we don't like to do that. Here's another example of some context effects. This is sometimes referred to as the Ebbinghaus illusion, named after Ebbinghaus. He was a famous psychologist in the 19th century who first came up with this particular demonstration. There are two central circles here. They're the orange ones. And they're each surrounded by gray circles. Do the two orange circles look the same size?
No, they do look different, but they're
They're the same size.
But I know you're trying to trick us, so I'm guessing.
Exactly.
Well,
If you're not expecting a trick, most people say that this one looks much bigger. It looks, but it ain't, okay?
But it's by comparison.
Yes, and, okay, so why don't they look the same size? Well, look at the context. The one on the left looks smaller because it's surrounded by bigger things. The one on the left looks bigger because it's surrounded by smaller things. How strong is this on the monitor? I'm just curious. Is it very strong?
What, the effect?
Yeah, it's the illusion.
Oh, it's really very strong.
Yeah.
The one on the right really looks bigger.
Definitely.
Okay, good. Interestingly, this occurs with vision, but not with touch. And I need to give you some background on that. Normally when people reach to pick up an object, their grasp aperture, how wide they open their fingers, is larger for larger objects. I mean, think about if you're going to pick up a pencil versus if you're going to pick up a cup. Well, if I showed you three-dimensional models of these, and then asked you to reach out and pick up the central circle, and I measured your grasp aperture as you did so, your finger position, it wouldn't matter if you're reaching for the one that was visually larger or visually smaller. You'd have the same grasp aperture. Now think about this a little more. The context influences your conscious visual experience, but it doesn't influence your non-conscious automatic reaching response.
So what's going on there?
Patience, young Padawan, patience. Next slide.
We're not to the zombies yet.
Well, yeah, actually, we've got a lot of stuff to do before we get to the zombies. You might think that given your visual experience, the grasp aperture would be smaller for the circle on the left and look littler and bigger for the other one, but it isn't. Context fools your eyes, your conscious visual perception, but it doesn't fool your unconscious reaching behavior.
It's very interesting.
This kind of dissociation has been claimed by some neuropsychologists to suggest that we have really sort of two different visual processing streams in the brain. So here you see a side view of the left hemisphere of the brain. Okay, the eyes at the lower left, back of the head is at the right. The purple lines indicate some of the major pathways between the eye and the primary visual cortex at the back of the brain. Now, from the primary visual cortex at the back of the brain, there are then projections that go forward in the brain. One of these goes to the temporal lobe, which is by the temples. Okay? And that's referred to as the ventral stream, sometimes called the Watt stream. You'll see the Watt label on the slide. That's the part of your brain that's thought to be involved in visual object identification.
Visual what?
Object identification. So identifying circle, ball, bell, not a bell, and whatever. The other major pathway is to the parietal lobe, this area. And this has been suggested to process information related to where an object is and how you would interact with it. Okay, that's labeled how, and then another projection up to is also labeled where on the slide. So you've got the one visual pathway that helps you identify what an object is. You've got another one that tells you how to interact with it. Now, think about the examples that we just gave of the circles. With one of them, you had to identify, which was bigger. But in the reaching case, you just have to reach out and interact with them. There is no visual system for walking backwards and stepping on things. Okay, so the Ebbinghaus circles also show us the importance of context. Here's another example of context. Which of these two gray squares is lighter? And you're going to say they're really the same, because you think I'm going to trick you.
No, I think the one on the right is lighter.
They're really the same. The darkness here makes this look lighter. The lightness here makes this look darker. Okay, this might not work because I probably can't blank out everything, but I'm going to try something. Okay, see how it's kind of different they look now with the gradient between them. Do the grays still look as different now that I've blocked out some of the gradient
They
between them?
don't look as different, but they still